Hello guys, welcome to the Parson series, and this is part 2 of chapter number 5. So if you remember, last time we discussed a lot of properties of the light and also the different kind of opacity media, how they were presenting the different properties like constructive interference, destructive interference, diffraction and all things. So today we are going to deal with the reflection. A reflection, what do you mean by actually reflection? Reflection means the bouncing back, and it is exactly the same thing that they are saying, bouncing back of light which takes place when the light meets the interface. So more or less at all the interfaces, whenever the light is striking, it will bounce back. Now this depends upon interface to interface, whether 2% is absorbed and 98% is reflected, or it can be 98% absorbed and 2% reflected, but some amount of reflection will always take place, starting from a clear glass up till the black curtain. Obviously, if you are using the clear glass, most of the radiations will be passing through, some will be reflected, some will be absorbed, but if I am talking about the black curtain, most of them will be absorbed. So the different proportions may be different, but some amount of reflection will always take place. All right. Now, let us talk about the laws of reflection. Now, for studying the laws of reflection, you have to consider the following rules. So, what are the three rules? The first thing is a normal. What is this normal? If you consider this ray diagram, this thing is actually called as the normal. Okay. So, normal is considered to be lying perpendicular to this interface. This is your interface. So, normal is considered perpendicular to the interface. This is your point number 1. Then number 2. Number 2, they are saying that we have got three things. One is your this incident ray. Then we have got this reflected ray, and the third is normal. All of them are lying in the same plane. In the same plane, you have got the incident ray also, you have got normal also, and you have got the reflected ray also. And the point number 3 is that the angle which is lying, the angle between this incident ray and the normal, this is called as the angle I. While if you consider the angle between the normal and the reflected ray, this will be called as the angle of reflection. This is R, and I will be equal to R. Very simple. We have got three rules. What is normal? It's an imaginary line perpendicular to the surface, then all three lying in the same plane, and the angle of incidence is equal to angle of reflection. Okay. Now coming to the reflection at an irregular surface. Now, whenever the reflection is taking place at the irregular surface, what is happening? They are actually reflected and scattered in many directions, and that is why it is called as a diffuse reflection. So, instead of using the word scattering, actually they are using the word diffuse reflection, but I think they mean one and the same thing. And this property actually they are using in the non-self luminous objects. So those objects, furniture, clothes, etc., where we do want scattering is required. In certain fabric also we require like multicoloring effect. So that time we are using the irregularities of the surface, and there we are getting the diffuse reflection. Okay. Now we are going to consider the reflection at a smooth surface, the plane surface, the concave surface and the convex mirrors. So first let us consider them in the plane mirrors. Okay. Now in the plane mirrors they have actually tried to explain this full ray diagram. If you are able to understand it, it's okay, but I think more important for you people is to go with the conclusion. So we can do it that the image of an object which is formed at the reflection on a plane surface has the following properties. What are these properties? Whenever we have got the plane surface, this image will be erect. Erect means the upright. It will be virtual and it is laterally inverted. Laterally inverted means it will be a mirror image, but it will be a virtual and erect, like that we were getting in the direct ophthalmoscopy, virtual and erect image. It lies along a line joining the object and the surface which is perpendicular to the surface. So if I draw a line joining the object to the surface, okay, then and this line is perpendicular to the object, so it will be lying along that line. Okay. And if you talk about the size will be equal to that of the object, and this image is actually located behind the reflecting surface. As the object is in front of it, the image is behind. That is why it is virtual, it is erect. And also, if a plane reflecting surface is rotated while the incident light fall on its surface center of the rotation, the reflected ray rotates through an angle equal to twice the angle of rotation of the mirror. Now, even they have talked about the rotation. They are saying that if this plane reflecting surface is rotated, okay, then what is happening? This light should be falling on the center of the rotation. Then the reflected ray is also rotating, but this angle is actually twice. This angle is twice to the angle of rotation of the mirror. So there are certain simple things that you should follow while we are considering the reflection on the plane mirror. Okay. Now, we come to the refraction. You have seen the reflection. Now we are talking about refraction. Light passing from one transparent medium to another of different optical density changes its speed. Now we already know that when light is passing through one transparent media to the another transparent media or a different optical media, then the speed will change. Okay, maybe a denser medium to a rarer medium and something like this. So this results a change in its direction of movement as soon as it enters the second medium, and this is called as a refraction. Refraction is the change in the direction of the movement. When the ray is passing from one medium to another and it is changing its direction. When it was not changing its direction, it was just bouncing back, that was your reflection. But if it is changing its direction while it is passing from one media to another, then that is actually called as a refraction. As in reflection, this thing will remain the same, that is, three of them will lie in the same plane. The incident ray, refracted ray and the normal, they all lie in the same plane. Now what will happen in cases of the refraction? So in cases of the refracted ray, when the incident ray traveling in one media such as air meets an optically denser media such as glass, what will happen? So again, important thing, what will happen here, it will now travel more slowly and the refracted ray will be deviated towards the normal to the surface. So one thing that you can take it as a dictum, they say that the greater the difference in the optical density between the two media, greater the deviation. So we already know that if there is difference in the density of the two media, there will be deviation. Greater the difference between the density of two media, greater is the refraction and greater will be the deviation also. So if the density of air is taken as a unity, then the ratio of its density to that of the second media is called as the index of refraction of that media. Now this gives a very important thing. We always study the index of refraction, refractive index. What is that refractive index that we have compared with the density of air? So we have taken the density of air as a unity, that is one we have taken, then the ratio of its density to the other. Okay, we are comparing every density with the density of the air, and whatever you are getting that refraction value, that is actually called as the index of refraction or the index of the media. Okay, now coming to the plane lamina. Now what they are saying, when an incident ray meets the surface of a plate of a glass with parallel sides, suppose a light is coming and it is falling on the surface which is having parallel slides. Okay, what is happening? It is deflected towards the normal. When the ray passes out of the glass on the other side, it will be deflected away from the new normal and it is also deflected towards it. So now what they are saying means the emerging light will be parallel to the incident ray but will be laterally displaced. If the plate of the glass is very thin, then this will be practically continuous with this Lm only. So incident ray is Lm. So they are comparing this Lm with the reflected light No. So how much diffraction will be there, how much deviation will be there, depends upon the thickness of the glass through which it is actually passing through. Okay. Now we come to the prisms, and I think this is an important thing because so many times we are using these prisms in the squint. So we have to apply this knowledge even in the squint also. Imagine that two sides of the plane lamina are meeting at a point A, okay, and we are forming a prism there. In this case, being similarly refractive with reference to the normals at these surfaces, now what is happening? The ray will be deflected along DEFG. Now let us try to see this picture 5.9. What is DEFG? DE, then we have got F, and then we have got G. Now they are saying that if I combine two plane surfaces at the apex, A suppose, then what it is forming? It is forming a prism. Okay. Now the rays are traversing through a path. This is your DEFG. Now what they are having about this DEFG. So what they are saying, that means because it is refracting through this DEFG, the rays thus deviated towards the base of the prism. So this means that this is going towards the base of the prism when the angles of incidence and emergence. Okay, now what they are trying to do, they are trying to tell you what is the angle of minimum deviation. Minimum deviation. So minimum deviation I am going to get when the angle of incidence and the emergence are equal, the angle of deviation will be least, and this will be called as the angle of the minimum deviation, and the ray is said to pass symmetrically. In these circumstances, if the prism is made up of the crown glass, the angle of deviation is approximately equal to half of the refractive angle of the prism. So some of the important properties of the prism itself, what they are saying, if the prism is made up of crown glass, then the angle of the deviation of the ray is equal to the half of the refracting angle of the prism. So different glasses have got different properties. If I am talking about this crown glass, in cases of crown glass, it is equal to half of the refracting angle of the prism, right? Now, objects are usually projected along the direction of the rays of light as they enter the eye, and in doing so, the effect of refraction may be ignored. If the light D is observed through a prism as in this. So, this is the light, okay, this is the light which they are observing. It will appear to come from edge. So, it looks as if when they are diffracting, now look at the path here. One is this, your this path, and another is this path. So when the light is actually coming from D, it is going and it is diffracting through DEFG. It looks as if it is coming from edge, but actually it is not coming from edge. Actually it is coming from D. Okay. So what is happening? It looks as if it is coming from the edge. Objects seen through a prism appear displaced towards the apex of the prism. So what is the one point that you need to remember here? That the objects which are passing through the prism appears as if they are displaced through the apex. Okay. Prisms may be categorized according to the apical angle or the refracting angle, angle of apparent deviation. So these are the different things that you need to remember in terms of the prism. Three things you will remember. One is your apical angle or the refracting angle and the angle of apparent deviation. Okay. Usually the prisms are categorized according to the prism diopters. This you know also. Usually we say which prism diopter is able to neutralize it. And one diopter indicates the strength of the prism, which produces a displacement of 1 centimeter of an object 1 meter away. So this is the theoretical definition of the prism diopters. If I am saying that this is having one prism diopter. Okay, so one prism diopter means that this prism is able to produce the displacement of 1 centimeter of the object which is situated 1 meter away. So likewise, if I am saying 7 meters, you can calculate likewise. Okay. Now talking about the lenses, what are lenses actually? Lenses are the pieces of glasses which are having the spherical surfaces. So the line passing through the center of the curvature, so whatever is the line which is passing through the center of curvature, this is actually called as the axis of the lens. So we have got various variety of lenses, like I have got biconvex, biconcave, plano-convex, plano-concave, convexo-concave, meniscus. So different kind of lenses are there. They can also have one surface plane, another which is curved at right angles. So different kind of any combination of the lenses. See, they have shown you different combination of the lenses. The biconvex, see, this is your biconvex, this is biconcave, plano-convex, plano-concave. So we have got different kinds which are possible. Now let us see the effect of a biconvex lens upon the rays of light. The effect of a biconvex lens upon the rays of light passing through it is very similar to what would occur if they were replaced by two prisms set base to base. What they are saying, that if I have a biconvex lens and I have to see what will be the rays of light passing through it, what will be the nature of that. So that is actually very similar. If I see the radiations passing through the two prisms, and these two prisms are kept base to base, so it will be very, very similar to that. And you know, whenever the things are passing through the prism, they are actually deviated towards the apex. Okay. Now, if the incident rays are parallel to the axis, they will be refracted in such a way that they all cross the axis through a single point on the other side. So this point is actually called as the principal focus of the lens, and whatever is the distance of this principal focus from the lens, so that distance is called as the focal distance or the length of the lens. So these are the certain, you know, things which you need to study. Like when we study the optics of the eye, the listings reduced eye, then these are the terms that we are using, the principal focus or the focal distance. Okay, when the lens has the same medium, such as air on each side. Now, if I am having a lens and both the sides I have air, that is same medium, the two principal foci, okay, the one on each side of the lens will be situated at the equal distances. But if I do not have the same media, then obviously the principal focus distance will change. Okay. For thin glass lenses of lens power, the focal distance, if I talk about the ideal condition, so ideal means a very, very thin glass. In that condition, the focal distance will be equal to half of the radius of curvature. So again, when they ask you about the most perfect combination, ideal conditions, when you are having negligible amount of thickness of the glass, then the focal distance will be equal to half of the radius of curvature of the two surfaces, and they should be equally curved also. So again, certain important things, because sometimes what they are doing, they are asking you numerical kind of things, and you have to apply these logics there. If an object is placed at a very large distance from the lens, very large means we are comparing it with the infinity. So if they are at very, very large distance from the lens, then you are considering them practically parallel. Till the time they are reaching the lens, we are considering them, then they are practically parallel. Hence, in this case, an image of the object will be formed by the lens at its principal focus only, because it is coming from very, very far. So we are considering that the image is formed on the principal focus, and this will be real, inverted and very, very small, right? So whenever the image is formed on the principal focus, it is considered to be real, inverted and very small. If the object is gradually brought nearer and nearer, the image will now recede further, further, further. It will grow larger until when the object is at the principal focus. So it is other way around. When the object is very, very far, you are considering the rays coming to be coming from the infinity, they are parallel, and the image formed will be what? Image formed will be at its principal focus. It will be real, inverted and very, very small. So now you are bringing the object very, very close, and therefore what is happening now, when the image when the object is coming very, very closer to the lens, the image will recede further and further from it, and now it will become very small. It will grow larger until when the object is at the principal focus, and till the time the object is brought at the principal focus, it will be increasing in size. Okay. Now the image will be receded to the infinity. Now and when the object is brought at the principal focus, then at that particular time what is happening, the image will go to the infinity and it will be infinitely large also. So this is actually the property of the image when the object is kept at different distances. Okay. Now we'll try to read the effect of a biconcave lens upon the rays of light. The effect of biconcave lens upon the rays of light passing through it is very similar if you are keeping the two prisms apex to apex. Like in cases of the biconvex, we were comparing them to the two prisms kept base to base. Now if I have something like this biconcave, so you have to compare them as two prisms which are kept apex to apex, something like this, and the rays will be reflected towards the apex. Here what is happening, if the incident rays are parallel to the axis, they will be divergent after the refraction, and the amount of divergence of the individual rays will be such that if they produce backwards, they will cross the axis at a single point on the side of the lens from where they are emitted. So what is happening now? Now they are going towards the apex. Okay. And what is happening, they will all cross the axis with a single point on the side of the lens. So it will be something like this. They will be coming on a point focus because they are going towards the apex. Now this biconcave lens also has an optical center. This optical center is situated upon the axis within it and having the same properties as those in the cases of the convex lens. Now I will tell you what is this optical center. If you see here, what is this optical center? We were talking about here. See, the point in the middle of a biconvex lens is called its optical center. So the properties of this optical center means the center will remain same whether it is the center of the biconvex lens or whether it is the center of biconcave lens, the general properties will remain same. Okay. So this was about your biconcave lenses. I think you have understood it. I have tried to make it simpler. We are not going into the much details, but whatever are the important aspects, we are trying to cover that also. Okay. Now we talk about the plano-convex and plano-concave. The plano-convex and the plano-concave lenses, they are acting like biconvex and biconcave lenses respectively. So plano-convex are behaving as biconvex, while the plano-concave are behaving as biconcave. So you have already dealt with the biconvex and biconcave, but the optical center for them is on the curved surface at the point where the axis cuts. But the difference is that here the optical center is not lying in the center, this is lying at the center of the curved surfaces. So it will be lying on the center of the convex surface in cases of the plano-convex, and it will be lying on the center of the concave surface in cases of the plano-concave. Okay. Now what is menisci? Menisci act as a convex or concave lenses according to whether the convex or the concave surface has the greater curvature where the optical center is outside the lens. In those cases where the optical center, which is supposed to be the center of the biconvex lens or the center of the biconcave lens, if it is lying outside, then that is considered to be as the menisci. Okay. It has been observed that the refractive power of the lens, if I consider the refractive power of the lens, that varies inversely as the focal distance. So again, important fact, okay, a lens with a shorter focal distance will have more of the refractive power, and because of its more refractive power, this will bend the rays more than the one with a longer focal distance. So it's very, very important, therefore, necessary to have some system of numbering lenses so as to indicate their refractive power. So for that we have taken one very convenient method, and that is the one which takes a lens with a focal distance of 1 meter as a standard, and such a lens will be having a refractive power of 1 diopter, because you know focal distance and refractive power are inversely proportional to each other. So whenever I want to find that how much amount of rays will be diffracted by this lens, I will be knowing by its focal distance also, I can know from its dioptric power also. So what I am doing, I am taking a lens of focal distance 1. Okay, 1 meter, that will be having a refractive power of 1 diopter, and therefore that will be kept as a standard. So in increasing order we can put from this, and we can put the decreasing order also. A lens which is having a focal length of 0.5 meter will be twice as strong as the one which is having focal length 1 meter. The refractive power will be 2 diopter. Similarly, if I am saying 3 diopter lens, then this will be having 1/3 of a meter. So this is very, very clear cut that the focal distance and the refractive power, they are inversely proportional to each other. So 1 meter focal distance means 1 diopter. Okay, 3 diopters power means 1/3 of a meter focal distance. 2 diopter power means 1/2. Okay, so I can say therefore what is the conclusion? Conclusion is that the dioptric power is the reciprocal of the focal length. It is important to remember in this system that the unit of measuring length is a meter, not a centimeter or a millimeter. Very, very important. Now we come to the identification of the lenses. Now usually if you go by convention, the convex lenses are indicated by the plus. That is why when we say hypermetropia lenses, we say they are plus lenses, while the minus is your concave lens. So there are several ways of finding out whether a lens is a convex or a concave and what is its refractive power. Now this is again very, very useful when you are working in the ophthalmic OPD, don't rely just on the colors. Even when you are sitting on the viva table and the lenses are spread in front of you, I know most of you actually recognize the colors. Red is for plus and black is for minus, or vice versa, something like this. But what is the simplest way? See, the simplest way of holding of getting this, that whether it is a convex or concave, what you can do, you hold a convex lens near up the eye and look at a distant object through it, and then move the lens a little from side to side. The distant object will seem to move in the opposite direction, so that in which the lens is moved. Okay, so what you are doing, we are bringing the convex lens in front and we are moving it side by side like this. So what you will observe, in cases of the convex lens, you will observe that the distance is moving in the opposite direction. Okay, like when the process is repeated with a concave lens, then the objects will move in the same direction as that of the lens. Now you will say, why this is opposite? We read this in hypermetropia that it should move in the same direction. So that is why its treating glasses will move the reflex in the opposite direction. Now what we used to study? We used to study that in cases of hypermetropia, if you remember, in cases of hypermetropia, it moves in the same direction. Okay, it moves in the same direction, and what we have to do? We have to neutralize it. So we neutralize it. Okay, we neutralize with the plus lenses. We are neutralizing it with the plus lenses. Plus is the convex. Convex is move in the opposite direction, so obviously it will neutralize and a time will come that no movement will be there. Similarly will happen with the myopia. Myopia, more than one diopter will move in the opposite direction. When I treat it with the concave ones, they will move in the same direction, and a point will come when neutralization will take place and no more movement will take place. Okay, the reason is that now you have already seen the properties that the convex lens forms the inverted image, where a concave one forms the erect image. So if two lenses of opposite signs but of the equal curvature are placed in contact with each other, then what will happen? The combination will make a plate with parallel sides, and there will be practically no deflection of the rays, and that is why you are neutralizing the movement of images, and that is actually the basic principle of the retinoscopy. So I think this is very, very clear. Now we come to the systems of the lenses, the combination of using more than one lens. So if you are using more than one lenses, that is the main funda behind when we are using so many instruments. You are using the combination of lenses, and we are using these combinations in such a way that you are able to get something out of it. So that is called as an optical system, and all the component lenses are centered on a common optical axis. So if all the lenses are having the same optical axis, then I will say that this system is actually homocentric, and you know, in this case the principles already discussed are additionally applied, but we have already read all these things. So when the lenses are in contact, the refractive power of the combination will be just equal to the algebraic sum of the refractive powers of the two lenses. So if I am talking about two lenses, so the capital D will be equal to small d1 plus d2, and if I talk about the focal length, then that is inversely proportional to the refractive power. So 1 upon capital F will be equal to 1 upon f1 plus 1 upon f2. So that is very, very simple. However, if we have got two convex lenses which are separated by a distance, suppose the distance between the two is C. The lens A will make parallel rays converge towards A, but after a distance C, they were meeting at B. Hence, the convergence of the rays by the lens A is not expressed by 1 upon f1. Rather, it will be 1 upon f1 minus C, because they are actually separated by this C distance. Therefore, what is happening now? The combined effect of the lenses A and B, D will be equal to subtracting this distance. So now I will have to add power of lens A, power of the lens B, and I will have to subtract C from the focal length of first one. This is again very, very important when you are considering this focal lengths, and you have to consider that you can just add on the two powers, or you can just add on the two focal lengths when you are having negligible distance between the two objects. So if you are having some distance which is not negligible, then you will have to subtract it from the focal distance of the first one. Okay. While if you consider the second lens to be concave, so if RB is concave, the effect will be one of the divergence. So now what will happen? Divergence means a negative one. Okay, now divergence means a negative one. So now when you have to consider the total focal, okay, distance, now you will have to subtract it. So if you consider here, where you were considering the convex lenses. So the two convex lenses were separated by a distance C. So what I was doing, I was adding the two focal lengths, but I was subtracting C from the first focal length. That was done. But now when I have the concave lenses, what I am doing, I am subtracting them. I am subtracting them, but what I am doing, again I am subtracting the C distance from the first focal length, but now I am not adding the two focal lengths, rather I am subtracting the two focal lengths, so that must be remembered. So that's all with the elementary physiological optics. We have studied all the ray diagrams, the type of lenses, the properties of the light. Now in the next of my lecture, we'll be talking about the optical system of the eye. We'll be utilizing these concepts and also seeing the clinical part of this optics and refraction, how we can apply these concepts over the actual eye. Thank you and happy ophthalmology.